Good morning, everyone. My name is Andrew Zhang, and welcome to my presentation. My research is called transformer-based meta-loss landscape exploration with actor-critic method. And I'm came from Hokkaido University, and these are all my collaborators. Firstly, these are today's topics. Firstly, I will make a brief introduction, especially about the gradient descent and the local minima and overfitting in the deep learning. And next, I will also briefly introduce about the loss landscape exploration and some related work. Next is our main proposal, which is TLLE, which means transformer-based loss landscape exploration, a transferable optimizer. And next is the result, especially the learning curve and quality and quantity result. Finally, is the summary and also future works. Firstly, overfitting is a well-known problem in deep learning. For example, if we have such dataset, which is D, and we have X and Y here, X is the input, or Y is the output. For example, in image classification, X is the image, and Y is the label. And then if we have a model, here F means the model, and X is the input. The theta is the learnable or trainable variable or weights. And if we have such a kind of loss function, which is L, and denote as this one. For example, L can be cross entropy loss or depth loss for the segmentation. Then we can use such kind of objective function and optimizer to illustrate the training process, which means by select the best data to minimize the loss function. And here we can use stochastic gradient descent to actually doing the training processes. However, when we are doing this schedule again and again, and usually we can find a very quite well-known phenomenon, which is as the training continue, the training loss finally becomes very low, and the validation loss it's become higher and higher. And this problem is called overfitting. And the reason of overfitting is described as the model memorize the training sample like this one, and can't generalize it on the test set. Currently, there are many works for solving the overfitting problem. And firstly is also the well-known method which named as data augmentation. And it is using some transformation to add more data or some to the train set. For example, like this one. If originally we have such kind of image, the image is a cat by a horizontal flip or vertical flip or some rotation. Even we can change the color channel of this cat because this type of transformation it won't change the meaning of this cat. So by this kind of transformation, we enlarged our dataset by 10 times. And the next is regularization, which is add some constraint to the objective function. For example, the L2 constraint or L1 constraint. And these constraints may also have some uh, they have some preset because they think the smaller the width, the it will make the model harder to learn to overfitting. And early stopping, this is very simple, which just stops the or stops training before overfitting. The next is dropout. And then this is randomly drop some unit during the training of neural network. But our question is, if we are, how do we avoid the overfitted minima that we already know? Our motivation is to try to learn from the loss landscape. The question is, can we benefit the next training step from the previous training experience? For example, showing this figure. Uh, for if we already know this black path, which is the previous training path, and next if we stand at this point, we no longer need to follow this path again, and because we know this landscape and we know this path, can we jump from this from here to here and converge faster? To achieve this idea, firstly, we need to know the shape of the loss landscape. Uh, so we come up with such a framework. We propose a student and supervisor model in this red figure. We define the model who learns the task as student and who learns the loss landscape as the supervisor. During each iteration, we add weights and validation matrix to this weight pool, or called replay buffer, and later used to train the supervisor. Then we could use the supervisor to help or guide the training of students. Okay. Actually, there are many works related to learning from the loss landscape. For example, stochastic weight averaging. Uh, they find better minima by during different training trajectory. They collect the different weights, and they find better minima by averaging the other minima, and expect to converge into a better area. And cyclically learning with scheduler. After overfitting, because the further training is useless, so they cyclically increase and decrease the learning rate because the larger learning rate will jump out from the local minimum, and by a small and by using but later decrease into a smaller learning rate will convert to a new minima, and by repeatedly doing this again and again, they finally will choose the best one. And then the next is training with flooding. What they do is after overfitting, they start to do gradient ascent instead of gradient descent, which I think has a very similar idea with the cyclic learning rate schedule. Okay. Here comes to our idea. Can we automatically explore the loss landscape? Okay. We can so our target is to maximize the future reward, and in this scenario, which is the lowest validation loss, can we maximize this future reward? Okay, to achieve that, we can change the direction. For example, we can change the different gradient. We can some new gradient rules, or we can use different order of samples, or we can change the index of batch samples, or we can even change the network structures. And if you know network architecture search, I think they are very related to this part. Or we can change the hyperparameters, for example, the learning rate or penalty factors. Okay, and this part will become very similar to the hyperparameter optimization. Okay, so how can we explore the loss landscape? Firstly, this is the naive SGD updated rules. Here, alpha is the learning rate, and in our proposed ALE, we replace the learning rate and hyperparameters by this actor-net. And in other words, we let the actor to select an action that can give a better reward in the training. Thus, our method can also be regarded as the B-level optimization method. In the inner optimization, we update the worker, and in the outer optimization, we update the controllers. Okay. This is the overview of our proposed TLE, and it mainly has three components. The controller who learns the loss landscape and give the gradient action, and the workers who actually learn on the targeted dataset, for example, classification or segmentation. And and uh, and then add the previous trained experience into the replay buffer, and use this replay buffer to train the controller. And by this framework, we transform the optimization in the loss landscape into a Markov process. In other words, a reinforcement learning task. And by the gradient actions, actually we have many kind of choice. For example, we can make it a learning rate scheduler or with regularization, or we can select the different samples, or we can do some augment method to this part. Okay, next come to our main experiment. Our main experiment is using a transformer-based model to do the segmentation. And this is the model we use for doing the segmentation. The model is, you can say, is a UNet model. Actually, it is a revision of the UNet R model. The original UNet R model is for 3D segmentation, and we replace the 3D convolution transpose layer by this 2D transpose layer, 2D convolutional transpose layer. Because it is a UNet-based model, so it typically has two components, the encoder and the decoder. So in this figure, the left side is a vision transformer-based encoder, and the right side is a convolution-based decoder. Okay. Here comes to our first result. The first result I would like to show is the transferable of TLE, which makes TLE different from other hyperparameter optimization or network architecture search method. Instead of the task transferable, we sampled a dataset, a subset from CIFAR 100, and transferred the controller from CIFAR 10 to CIFAR 100 subset. You can see the training speed increased and also from the similar scheduling curve. From this figure, we can conclude that due to the loss landscape of two ResNet and similar for the CIFAR 100 subset and CIFAR 10, TLE can be treated as a weight level transferable optimizer instead of HPO method. And this is the training result of the segmentation for the workers. This figure is the training losses and the test losses as a learning rate scheduler. So here LR means the learning rate scheduler and RE means penalty factor scheduler. So how does the controller adjust the learning rate? From this figure, we can see. Yes, it converts back by tuning the learning rate scheduler, it converts lower. And here is the regularization penalty factor, and by tuning the penalty factor, and the overfitting problem become less. This is the segmentation result we get from a pathology dataset. And this pathology dataset is a high resolution dataset. You can select the different resolution settings, and for example, 8K, 4K, 1K, and 512. And the size of sample is 260 in total. During our training, we use about 75 for training and the left half for validation and the rest for test. The result is quite clear. TLE helps find better result than the baseline. And I think not only the shape, but also the detail, they are more accurate. Okay. The next result is a quantitative result. Not only we do the experiment on the PIP dataset, we also doing the classification task on these three dataset. But we do this by changing the complex decoder of the unifier model by a lightweight linear head to do the classification. And you can see our experiment has been conducted across the MNIST dataset, CIFAR 10 dataset, and CIFAR 100 dataset, and they are commonly used and also other commonly used models include MLP, include VIT and ResNet. We also replaced the decoder header by a single classification layer. You can see with the help of DLE, the result is better. Okay. The last one is the limitation of the method and also the future direction. At the beginning, we want to generate the gradient instead of tuning the learning rate. However, the gradient is much more difficult to generate. So the future work will focus on how to design gradient instead of selecting hyperparameters. Okay. Here is the remarks and future works. Firstly, we conclude with a weight level transferable of the measure, which is TLE, and it could automatically schedule learning rate and regularization. And the limitation is firstly the overhead of the controller. The cost of the controller is higher than the atom optimizer, and later we will come up with a end-to-end model. Next is the sample efficiency. The training because the training of the optimizer costs a lot, so we need a better RL algorithm and model. Okay, and that's all. Thanks for listening.